Okay, cool. So we start? I start? Yeah, sure. Cool. So hi everyone. Let's talk about containers, virtual machine, and all the things. For those who don't know me, my name is Quentin Adam. It will be better that way. So my name is Quentin Adam. I have a weird pseudo on Twitter, but it's available everywhere, so it's cool. Except on Pokemon Go. If you find the one who just stole me my nickname on Pokemon Go, I want to have a discussion with him. So basically, my job is to manage a company called CleverCloud. CleverCloud is an IT automation company. So what we provide is a very simple way to people to just like push their code and it just run. So people just use us to keep their apps online. They push on CleverCloud the code, and we make it run, and the application is not working, and we manage a security fix, auto monitoring, auto healing of application, auto scalability, auto everything basically. And it's a very cool company because we have customers in 1,700 cities in the world. Big customers, small customers, like small startups, banks, very different way to interact with us. And we try to learn a lot of what they do on their work and how they interact with us. And we try to give back to the community what we learn. So this is a big picture about Clever and who I am. So why are we speaking about virtualization, container, and all the stuff? At the beginning, computer was very giant hardware, like this room of hardware, but basically weren't able to calculate a lot of things. The capabilities of the hardware were very slow. And to run many software on the single hardware, we have to manage stuff. And it leads to have a multiprocess. Multiprocess is the time where, at the beginning, the computer was just the place where we put things, and the software was running, and we have the answer. And then the hardware become more and more powerful, so we need an operation system to manage the software we ask question to. So we need to create the operation system to have multiple processes inside the hardware. And one of the bigger things become the process scheduling. Process scheduling is really, really, really complicated stuff. It's all we do to manage to have multiple processes in the same stuff. Sorry, I lose my mouse. Okay. And then we invent Unix. Unix is what? Unix is the ability we have to learn how we can make an operation system work in the good way. So Unix has done a lot of stuff about how to manage multiple processes to run along each other, but it leads to the spaghetti operating system management. When I speak about the spaghetti operating system management, I want to speak about like 15 years ago when I'm doing some ops system. We have the servers, and we basically install all the stuff inside the same servers. And the documentation of the servers was the ops who basically installed on the servers. And there was weird interaction between several databases, application servers, and stuff like that. And it's blow up like every time. And we're just like, okay, what we can do to improve that. So we start to We start to find a way to unlink the hardware capability of a server from the software we need it at a precise point of the time. And to do that, we have the process. Process is very interesting because process allow you to just like what will be the next thing you will need. So just giving you an insight about what we can use as process. No, not at all. Process. I will start quickly a virtual machine, and inside it we will, work with process. No, we don't. Just Vagrant up this. Okay, cool. Launch it. I just need it. So the process is cool because every application run inside its own process, which is very important to be able to not kill others' application and not interact with the memory of others' application. I don't know if you remember in the 19th where we can interact with the memory of others' application, just putting some memory inside it. So process is cool because the operation system allows you to be sure that nobody is touching the memory of another process. It's basically how it works. So when we go inside this, I have write a bag of node.js script we need, and we can use it as if I start the server 1. So we have a server running there. And if I curl it, you're able to answer me something. Cool. But the point is, admitting we have a problem on the server, we can exec stuff running from this node system. And for example, we can ask for date to be executed, or more, we can just change what is the file system. And with it, the problem is the file system is accessible because the process is not isolated from the other part of the operation system. So we started to think process is cool, but it's a lack of isolation. Sorry, I try to not. Okay, cool. Isolation is primordial stuff. First, there is a software dependency. Did you remember being mandatory to reconstitute all the dependency of your system using aptitude, because basically software A need libxml2 at one version and software B need libxml2 and another version? This is a problem of isolation between the two software because you need the dependencies of the system will be isolated and not binaries for the whole system. The other point of isolation is about the security. Like I prove, the problem if a process is available to just like enter and write some data everywhere in the system, we will have a problem. So we need to secure a process to be sure it's contained at what we do. And the hardware resource access. We don't want an application can hit the whole hardware resource access from all the users' application at one time. And these 3 points are basically what we need on the isolation part. To do that, we're starting to work on something called chroot. Chroot is something very early, built on the 90s, but it's very interesting because it's allow you to just use what you need at a precise time to isolate your process. So basically what we can do is we will mount a chroot system inside the system. So first I will kill my first application and go on a base system I built here, we build a chroot system. And first, we need to be root to do that, because chroot need a lot of stuff built in to be root. So, I'm inside a chroot. So basically, if I do ps-ox, I'm still on the hardware. But if I'm looking on the stuff, I will. Where is? But anyway, it's not the point. I'm inside the chroot. What is really interesting is I can chroot another thing inside. Like for example, I say I will chroot inside this new file system. So basically, the Unix point of view was all is on the file system. If everything is a file, if I change the root file system, I will change everything about how works the system. So basically, if I say, OK, I will need to do a system with, I can use chrooting inside it. And I use this to connect. I will create a system which is isolated inside a chroot system, which is kind of different system. So if I look at it, there, my node.js is still really completely isolated inside each chroot. And if I try to do the same thing like before, for example, my exec stuff, there I can see I am inside the chroot. And if I want to create something, it will not do this inside the real root file system, but it will be inside. It will be inside the chroot file system I have created here. Okay, so I kind of isolated. The problem with chroot is it's really dangerous, because chroot is built inside the system to be available to be chrooted from another chroot. So you can chroot to be chroot to the prior version of the root file system. So basically you can unjail yourself and go back inside the root file system. And this is a very big problem because you are mandatory to use root, and anyway you will have a lot of capability. So the problem with root downside is there is this weird relationship with root. There is easy to break out, and more, if you create a new password file inside your chrooted file system, you will happen to have a situation where you can maybe be able to log in as root in the first system without to be root because you change the way it's interact. To be sure it will not happen, the way PAM and other stuff inside the Linux need to be patched to manage the chroot system. And it's one of the biggest issue with this kind of stuff. It needs the whole GNU system to be patched to work. And there is no depth management like really, and there is no hardware resource management. So basically, that's why people jump to jails and containers. What is jails and containers? It's all this stuff you have heard about before. apt-visit, Linux web server, LXA, and the new hype with Docker, runc, Rocket, and all the stuff. And the point is, all of these are only used Linux kernel as a runtime. You don't have like real difference of how these things work, except of how you access them, how you start them, how they can get their dependencies, but basically the runtime is the same for everyone. It's just the Linux kernel. Basically, a container system is chroot plus Linux namespace. Linux namespace is something introduced first in like 15 years ago in the Linux kernel for chroot, and it's an ability to make a map for a process of this, you think of this name, knows this name, is an alias map of many resources on the system. The mount resources, because you need it on chroot, which is the ability to change the architecture of a file system. The PID, so change the number of PID of the old architecture just as a point of view for the old file system. The user, the network, the IPC, the date and time, and all of this, you can just switch it to a new, it's just a map of traduction just for the process you need. And the other point is the C groups. Many people think C groups are security. It's not security anymore. C groups is more a possibility to check what is the hardware resource consumption inside the system. And it's the ability to just manage the resource consumption of the system. It's made like more for quota on resource consumption. The other point with Linux C groups is it's not perfect. It's not working like at perfection because the Linux kernel have to be the judge and the executor on the same time. And it's not like real time. So it can be possessed by a process wanted to use 100% of the CPU because it cannot measure it at the same time. So it was a problem with Linux C groups. And fun. And the Linux capabilities. Linux capabilities is, there is a setuid thing inside Linux. Setuid is the ability to say this program will use some ability of high-level permission for root. But the point is, setuid gives you the access to everything. So people inside Linux kernel thinking it's not a good idea. So they start to try to slice the authorization of the kernel into more small parts to be able to just like give small parts of authorization to each people. And the capabilities are basically that, is the ability to give like just some capabilities of the root users of the main access to some programs. And it was thus the Linux capability which is on the heart of the container security. So just to be clear, when we see containers, people are seeing, a giant metal box and wrapping things inside it. But no, a container is just a Linux process along others Linux process. So if I try to just like, okay, I am running some containers in this machine. And if I want, I can do, I go inside a new container and I start an Ubuntu with a bash, okay? Inside it, if I do ps-aux, I see I have a bash and I have a process aux and everything is okay for me. But now, just taking some time, we will go inside the Docker for Mac shell. So yes, for people who don't know it, Docker for Mac is not native. There is hypervision. And Docker for Mac is using Linux underlying, and the Linux underlying is there. Oh, cool. What's happening? Cool. Maybe it's because it's too big, you know. Okay, so that's fun. So anyway, this is the Linux underlying inside the system. And if you're looking at this, you have all the process running there. Okay, I will start everything inside another system, like sorry for that. Docker messing around. I think I have many Docker machine available. Yep. So basically, I have some processing, some things here to work, and I can run something like Docker run Cassandra, just to be sure we have many process running. It will be just a little bit time to just like catch the old Cassandra images. No, can you take it? No, you don't want, because, you know, too complicated. I don't know why it's so broken here. Parce que je l'ai encore d'ouvert ici. Very weird. Maybe it's open something. Ah, yeah. I think here. So, no, not yet. I have to find everywhere where there is a screen open, and it will work. But anyway, so your Docker is running, and if I do a pass aux system, what we can say is there is all the stuff running inside your container, and there is just only process along each other. So it's just Linux process with special permission. The problem with this is the isolation, and the side effect of the isolation will be not so good. Just explaining you what we can be happening is, so for example, I just run inside the Ubuntu I start there, but what I can do is launching just a fork loop, just to give to the container a problem to manage. The problem is, inside an operating system, you have a number of file descriptor. File descriptor is something created each time you open a file, and as you are in Unix, everything is a file, so each time you have a process running, you have a file descriptor. And the point with file descriptor is you can add unlimited file descriptor append. So you will have a number of file descriptor you can have. And the point is, this number is shared in the whole operation system. So what's happened there is, if I go inside the Linux system of the Docker for Mac, and I try to have a Docker ops, I see there is a lot of Ruby process running there, and in just a few minutes, I will not be able to. I am not able to do that because it's still okay. The problem is file descriptor are putting more and more. I will not be able to open more file. So I will not be able to open a new SSH connection. I will not be able to use a new command line inside it because the file descriptor resources will be full at the whole operation system, which is one of the side effects of using a whole operation system for things you think it's really separated. Another side effect with that is you can escape for a container. If you go and watch this YouTube video, because the hack takes a little bit of time, you need to re-encode things inside the memory and stuff like that, but you can escape for a Docker container and go back inside the host because Docker container rely on only the Linux kernel to be safe. And the problem with that is if you have an issue inside the Linux kernel, you will be able to pop up to the Linux kernel and to the host like from yourself without a problem. And it just happened like .eco was 2 weeks ago. And it's an issue inside the Linux kernel who is able to give you some privilege escalation stuff. And this is one of the biggest problems you can have with your containers. But there is many ways to make your system with a problem. For example, inside a Docker host, all your container will share the same source of entropy. You know, entropy is the ability to have some random numbers. So if everyone is using the same source of entropy, you can have situation where you can predict what will be the next random number for all those containers in the system and basically crack the crypto inside the system. And there is many other system-wide possibility of fails because what you are running there is using Linux at the boundaries of what he is doing to do. Launching thousands and thousands of processes in the same time, very different with different binaries, is really, really, really stressful for the system. So you will have a problem at a time. And that's why, and this problem is mostly the same for everyone on the container way. The other part is more like for Docker. Do it respect the Linux philosophy? When we created Unix, we say, okay, it will be KISS. Keep it simple and stupid. The Docker binaries today is a reverse proxy, an orchestration system, system will launch daemons, an ability to manage containers. I don't know if it can brew you coffee, but you know, it do everything. It's a fat binary of 40 megabytes, and we're just like, okay, what it can do more? Is it a really great idea? Is this the same people to say to me, you need to do some microservice and have only fat binaries who do everything? And the other problem with the managing process. One of the problems with Docker is he managing the process inside the operation system like he was the PID one, but it's not the PID one. So basically they fight with systemd all the time to managing the process. If you want to managing the process, it's okay. Just launch and stop the process if you please to do that. The problem is managing the process is not the only role of the PID1. PID1 have to clean the zombie process too. And it's another problem. Inside the container, the process you launch first think is the PID1. So basically nobody inside the container is in charge of cleaning the zombie process and all the weird stuff PID1 is doing. So basically, you are just running an operation system without a process manager. And I think it's a big problem. The other part is a container is all the operation system except the kernel. When you use the glibc and other stuff like that, it interacts a lot with the kernel. And when you use Docker saying it will be exactly the same thing running from the developer computer to the production, it's really not true, because on the computer you're using the Linux kernel of Docker for Mac, which is pretty particular, and when you're running on the production, you're using I don't know which kernel, and you will put in production untested combination of glibc, kernel, and all the low-level stuff. So I think it's a little bit complicated. And the other part is the monitoring. You cannot monitoring a container from inside it. You need to be outside of the container to understand what is running inside. So you need to rebuild the old monitoring system to be able to reconfigure in all the time. So it's complicated. We are in the boundaries of the Linux system. It's really complicated to just like manage that in the right way. So the search is not over. When we are looking for what will be the next thing in the emulation way, there is one guy who have write QEMU. QEMU is something very interesting, which is able to emulate a full CPU inside another computer. So you have a software CPU, and you can run another operating system on top of it. And it's very cool, because it seems to have a new CPU, so you have basically an entire virtual computer inside your computer. Then, from another perspective, others guy at this time working on Xen. Xen was the para-virtualization stuff. So basically, they write a very tiny kernel, tiny operating system, and they do a big patch inside the Linux system, and you will able with Xen to launch a Linux kernel to just like run stuff on Xen. And Xen will allow you to have multiple Linux kernel running on the same CPU stuff. And stuff become faster when Intel introduced new instruction of the CPU called VTX. VTX is a set of CPU instruction who give you the ability to run two operation systems on many operation systems on the same CPU without they know each other was running. So the virtualization is not about software. It's about hardware. And what is cool is the VTX allow you to just run some operation system who don't know others are running among each other. And a VTX can control the access to the hardware. When Intel created this at the beginning, they were showing you big computer with only one CPU and many network cards, because they're thinking people will buy a network card by virtual machine. But basically, it's not like this. We have an internal network stack, and we use the same network card for everyone. But the basic idea of Intel when they do that was using plain old operating system inside the same physical hardware resources. And when we have looked at that, it's really interesting, because the isolation and the VM perspective is you have the full software dependencies, because you can have a full operating system for your application. There is a full security system, because the security is guaranteed by the hardware, and the hardware resource access is guaranteed by the hardware also. So the isolation is perfect. So why we don't use it? Because people are speaking about performance. Who think virtual machine is slow? Because you're using Amazon Web Service. Starting a virtual machine inside Amazon Web Service is taking you several minutes. At Clever Cloud, when we start a virtual machine, from the moment we ask the orchestrator to boot the virtual machine to the moment the virtual machine starts to work for the customer, it's only 5 seconds. You can have really fast virtual machine. Virtual machine can be really fast if you're doing it right. And the point is that, with performances, is what is the really bound you have? Many people think CPU is important, or RAM. People thinking the RAM is important. But we don't have problem of boundaries of RAM anymore. We have memories. It's not a problem. The CPU is not a problem. To burn your CPU, you have to get really complicated stuff. So the problem is the input-output system. And the input-output system, the storage and the network, is where we need to have performances. And it's basically where virtual machines are very present, because there is a native system using directly access to the hardware you can use on virtual machine. So just choose what is your fight and starting to learn something new about the virtual machine. The other part with all of this is the Linux low-level dark magic. Many people using containers have surprises because there is many low-level dark magic inside Linux. And containers using a lot. Like, for example, speaking about Alpine Linux. Do you know Alpine Linux? Do you know why Alpine Linux is so light? No? Alpine Linux just rewrite the glibc, you know, the library everybody is relying on, is rewritten by the people of Alpine Linux, first on microclibc and now on Muzzle. So basically, when you're using Alpine Linux, you're just using another central part of the system nobody is testing the software against. For example, in the Java community, nobody is trying to compile the GTK with Muzzle because we don't care. Muzzle is just written by, I don't know, 10 guys. So it's a dark magic of Alpine Linux. And you need to be aware of this kind of stuff. The other part is the dependency limit monolith. If your dependencies are managing stuff to be like, if you have some dependencies, you have to maintain it. And if you think about it, if your code have some dependencies, it's cool, it's your code. But if you have the libraries as dependencies, it's okay. So you're doing a Spring Boot application, you have a Gradle build stuff, and all your dependencies are there. Why putting the whole responsibility of the OS to the Gradle dependencies? Because what you do there is asking the developer to enlarge the full stack of dependencies to the whole operating system. And for this, the problem is developers don't do updates on libraries. Why they will do updates on the operating system? This is dangerous. And if you're thinking about that, is if you're using container that way, you're just using giant binaries everywhere. So just to be clear about something is, they will never have something like Docker for Windows running Linux containers. You can start a virtual machine inside Windows and run Linux containers. But as Docker is not semantic, Docker is not knowing what is running. It's just a giant binaries at each time. You will never be able to run the Linux binaries inside the Windows because it don't work. And it's exactly why when I see Docker for Mac is native, it's not real. Docker for Mac is using a Linux kernel underlying inside a very clever and a very amazing piece of technology, which is the virtualization of Docker for Mac. Because this part is really amazing. But it's still virtualization because you need a Linux kernel to be able to run your Linux binaries. So just to be clear, it's just giant binaries everywhere. And the other part is just like, when you're thinking about going to DevOps, DevOps is not developer making the job of ops. It's developer working with ops. when you go in the 12th century in a castle, there was one man. This one was the man speaking Latin, going alchemist, and which was a doctor. Basically, it was knowing what humanity and all the mankind was knowing. But if you're going today to have a brain surgery, launching a rocket on the moon, or fixing your car, it's not the same people you ask. Because it's not the same job. As developers, making the jobs of ops is not the progress, it's a regression. It's against the history. History going to specialization with people knowing better the stuff, not people doing the job of many others. So when you do DevOps, it's not like developer putting Docker in production because I don't want to work with ops, so just put Docker in production, I don't care. Because you will have a problem. So please remember after this talk, containers and virtualization is not the same thing, and containers are not light VM at all, and it will be really dangerous to think that. The container isolation is not okay for running third-party code, and it's basically like running large PHP Mewtwo shared system. You know, you can buy it for at OVH for €1 per month. And if you want to be a Docker specialist, no problem. Just start reading the kernel release note, because you need to understand how the Linux kernel is working inside it. So thank you a lot for listening to me. And if you have some question, I'm here.